Hello all, welcome to the second part of this RNN tutorials in which now we will be looking at the implementations of RNNs, LSTMs and GRUs. I'm confident that you are comfortable with uh, the equations and the sizes, the matrix sizes of the weight matrix sizes and bias sizes, and then you are comfortable with the transformation. And then I'm assuming that you are comfortable with the idea of recurrence in GRUs and LSTMs, and also the multiple layers that are there in a deep layer RNNs, LSTMs, or GRUs for that matter. Now we will see all of them implemented now using PyTorch. Okay, so let's start with that. Let's take first, let's put all the input and other things together. We are generating a dummy input and then we are going ahead with that. So now the torch is the base package, NN is the neural network that is needed for us. Now batch size is 2. So the sequence length, that is the how many inputs are there is 5. Okay, that is your capital T is 5. Your input size, that is the dimension. Now in this case, D is 10, and then the hidden size, which is the H. Okay, this is 8, and the size of H RH, and then the number of classes is 4. Okay, now that means that you will be only looking at the last output, which is there, and then using that last output, you will be going ahead and obtaining the number of, you'll be going ahead and obtaining the final decision. Okay, so now I'm generating an input which is a random batch T, which is the total sequence, and D, which is the dimension of it. Okay, so you have the input which is 2 cross 5 cross 10. Okay, so now what will be the hidden thing? The last one now will be a size 8. Okay, this is your H capital T. Okay, now that will be of size 8, and all your intermediate outputs, which will be there, that will be 5 cross 8. Now, because for all the 5 examples, you are storing the intermediate HTs, therefore it will be 5 cross 8. Okay, so and then you have 2, so it will be 2 cross 5 cross 8. Okay, now you should be able to and you should be able to convince yourself that okay, the input size and the output size should be visually appealing. Okay, so now yeah, you create an RNN classifier. Now this has to be a child of NN dot module, exactly similar to the MLP and CNNs that we saw. And whenever you're creating, what is the input size? Okay, what is the hidden size? And then what is the number of classes? Now, why do we need them? So now let's go to the RNN. Okay, now if you look at it, now input size, your D is needed, hidden size is needed. Okay, and what is the output size? K is needed. So only when you have those numbers, now that is when you can define all these weight matrices. Okay, so you need these input. Now in our case, now H is 8, D is 10, K finally you will get it as 4. Okay, this is what now we have. Okay, that's what. So you are creating an thing which is input size is uh, what is the input size is 10. Okay, that is for one given sequence. Now you have 5 timestamps like that. Okay, now that the same thing will be unrolling, correct? Now the parameters will be shared across time, so you should be able to remember that. So and then the hidden size, which is 8. Now batch first. What do you mean by batch first? Now as I told you here, in the data, okay, the first dimension actually corresponds to the batch. Yes, it is true. And then finally you get an output, which is your HT, which is there, that you have to convert it to the final outcome. So you need an MLP to convert it into number of classes. This is 8 cross 4. That will be a fully connected layer. Okay, this is only done for the last one. Okay, so now let's try to understand this. Now first you have the input. Now I have given lot of prints so that it is easy for us to understand the output transformation which is there, because which is very much important. Okay. So first is the input shape. So the input shape will be BTD. Okay, now this is 2 comma 5 cross 2 comma 5 comma 10. Then you pass that through the RNN. Now RNN will give you HN, which is the last. This is your HT. That's what it means, that the last one. And then this output which is there is the combination of all the states. Okay, all the states output. So this will be the output, will be of shape BTH. Now that is 2 comma 5 comma 8, which makes sense. And then your HN, you have only one layer, so it will be how many examples are there, and then the hidden state of it. Okay, which makes total sense. And then what do? You take the last one, you take the last hidden state, that is H capital T, and then you pass it on. You get this. This will be in the form of B cross H. Then you pass this through the fully connected layer, and then you get the logits. And then you have these logits, pass it through the softmax, you get the probabilities. Okay. Exactly the similar one. You create an instance, and then you generate the input and pass it on. This will give you the output. Okay. It's allocating the runtime. This is how once we know the input and output relation, it is easy for us to traverse. And this is how we do it. NN.RNN is how we create the layer. Okay. As you can see here, RNN output is 2 cross 5 cross 8, where which all the outputs that are there are being stored. And then your HN is the last HT. Okay, that's what HN means here. And then that is 2 cross 8. For each of those examples, 2 is the batch size. You have an 8-dimensional vector. And then the final, that 8 is passed through fully connected layer, which is kind of transformed into this. And this is your logit. See, your logit has a negative number. It's totally fine. Your softmax cannot have a negative number, but logit can have a negative number. Okay. Now, this is regarding a simple RNN. Okay. How do you define a simple RNN? So we are still, no, you don't need to write anything for recurrence. Okay. The recurrence in terms of time, the unrolling is taken care. Okay. Now, depending on the number of examples that are there, that is the capital T, which is there, based on that, the recurrence is taken care. Okay. Now, the recurrence is taken care. You just need to define the whole structure. Now, this is weight sharing. The parameter sharing is across the time is there. Okay. So now let's look at the same thing as LSTMs. It's exactly similar, but in LSTM, rather than having only hidden state, you will also have the cell state or the candidate state, which is there. Now, all of them will be of the same shape. So the shape consistency is there. So as we have seen in our earlier discussion also, simple LSTM classifier, it has to be a child of NN dot module so that you can have the automatic differentiation taken care of. But then you have ln.lstm, that is there, input size, hidden size, batch first is equal to true. Exactly the same thing. Okay. Now here, whenever you pass it through the LSTM cell that you have, no, you not only get HN, which is your short-term memory, you also should get your CN, which is your cell state, CN, but both of them will share a same size. Okay, will be of the same size. And then output is there, which is accumulation of all your the previous states. Okay, so then you just get this, and then you get the last one, and then pass it through the fully connected layer exactly in a similar fashion. So this is how you have your simple LSTM classifier. Okay, I'm just having one cell. Okay, I'm not going ahead with the deep. We will discuss how to go into the deepness. How do you implement the depth which is there. Now, similarly, GRU is exactly similar. Okay, only the internal operations will be different, but the way in which the structure is there, it's exactly similar. NN.GRU, input size, hidden size, batch first is equal to true. You create it, and then you have a fully connected layer so that you have the final output is converted into a posterior for the sake of classification. And the outputs, all of them will match. I'll not be going in deep with this. It's exactly similar to the RNNs and the LSTMs that we saw. Okay. So now comes the important thing. Now, which is okay. Now, this makes sense for us to deal with the classification problem. But what if we have to take into consideration the sequence to sequence generation? Okay. Now, in that case, you want to many RNNs. So, exactly similar, but one major thing that is the difference is you will not be only passing the here to the fully connected layer, you're only passing the last one, correct? You're only passing the last one, but here you are passing the full thing itself. Okay, you're passing the full output itself. Now the nn dot linear will be hidden size comma output size. It will take each of those output and then apply it, and then it will give you an output which is b, which is the batch size t. For each sequence you can index them, and then the output size. Now we have taken output size to be 6. Okay. Now that will be 2 comma, this is t is 5 comma 6. Okay, that's what you will get. Okay. So you have the output of each of them, pass it through the fully connected layer, where which you have 6 classes. Now then you can choose, put a softmax over there, and then choose the highest argmax. You can do it and choose the highest probability. Okay. That's what 2 comma 5 comma 6. Okay. The main difference is you'll in whenever you are going ahead with a classifier, okay, you'll be passing only the last HT you'll be passing, but here you'll be passing the whole output itself, where in which you have all those individual contexts are there. Okay, that is the many to many, that is a sequence to sequence idea which is there. Okay, and please remember that in all these cases we are dealing with only one layer. We haven't implemented multiple layers. Okay. Now, whenever you implement multiple layers, then so you will be having these kinds of connections. Now, if it is only RNN, no, now you have this. This will be passed to the next case. Okay, and then you will have the MLP at the top. Okay, now that is fine. Now here you have two, there you will have only one. Fine, good. So now then how do you do it? See, the idea is very simple. Just use the number of layers, 3, which is there, and then while defining the RNN block, you just specify how many layers you need. Okay. So now, because of which it will not only, if you don't specify, number of layers will be considered as 1, so you only get 1. If you specify the number of layers, you will have this. So till here you get it, and then you use the FC to use this. Now all these parameters are actually shared. Okay, now you just do the same unrolling over time. So and then linear, you have hidden size to number of classes. Okay, so now what will happen is, now whenever you want to get the last one, now you'll not be getting last one of only the one layer. You will be having HT of all the layers. Okay, that will be one difference in terms of the HN output. Okay, so now you get two outputs because of RNNs, you get three outputs because of LSTMs, you get two outputs because in GRUs. Exactly the same way in which you have done in the RNNs and LSTMs. It's just a simple extension of the same thing. Okay, but you just need to specify the number of layers. Now, because of which the size of HN, which is there, will modify. Okay, now here output. Now, whenever I'm saying the output, that is of the last layer. That's what is happening. Whenever I say output, that is of the last layer. Okay, but whenever you say HN, which is there, which is the last hidden state, that will be for each layer. You will have a different hidden state. Now, all of them has to come along. Now, what is that I'm saying is, when I say output, I only say the last one. Okay, whenever I say the hidden state of the last unrolling, no, for each layer it will be different. No? Correct. That's what I need to get. Okay. So now this is your last HN. This is you can equate it to the y t at each time step. Okay. So this is your h capital T. You can get it, and then you obtain the last y which is there. Okay, the last one, and then you pass it on through the fully connected layer to get the final output. Okay. Now exactly a similar structure in LSTM also, deep LSTMs. You just specify number of layers here, how many number of layers you want. Now because of which the same will be the case for short term and long term context, which is there. And the output generation is exactly similar. No. Okay. Even in the case of deep GRUs also, you just specify the number of layers. Okay. And then you can get the inputs in a similar manner. Now, this is how you actually implement a classifier or many to many problems in using LSTMs, GRUs, and RNNs. Okay. So I hope you will be comfortable in implementing these things. We will meet in the next tutorials, wherein which we will look at the thing that changed all our lives. We will be looking at how do we implement the transformer model. Okay, the transformer architecture, how to implement that. We will be looking that in the next tutorial session. So I hope all of you are on your feet. We'll meet in the next tutorial sessions with the transformer architecture. Till then, have a nice day. Bye.